Okay, welcome everybody. So today it's our pleasure to have Minghui Diao giving the EOL seminar. Minghui is currently a postdoc here at the ASP, and we have the joy of working with her out at RAF and within EOL. Minghui got her undergraduate study at the School of Environmental Sciences and Engineering in Peking University in Beijing. In 2013, she received her PhD from the Department of Civil and Environmental Engineering at Princeton. And during her PhD work, she has been involved in quite a lot of field campaigns, primarily with the NSF G5 aircraft, such as HIPPO campaigns, DC-3, PREDICT, etc. And she has a long list of fellowships and awards before coming here, and they include a NASA's award, and Space Science Fellowship, Francis Upton Fellowship, Waldridge Graduate Award, Princeton Energy and Climate Scholars Grant, and the Outstanding Paper Award for both the AGU 2009 Spring Assembly and the AGU 2010 Fall Meeting. And even if my name is listed up there, I have to say that this is really Minghui who is the driving partner of it. So here you go, Minghui.
Thank you, Jan, for introducing me. Hi, everyone. Welcome to my talk today. So if you don't know me yet, my name is Minghui Diao. I'm an ASP postdoc hosted by EOL Division, and my advisor is Dr. Yang Jensen. So before I start my talk today, I want to acknowledge all my collaborators. That include Dr. Laura Pan, Eric Jensen, Carmen Holmeyer, Sean Honemish, Jim Bresch, Andy Himsfield, Aaron Bessemer, George Brown, Hugh Morrison. Also, the instrument PIs, the science teams of Starlight campaign and the HIPPO Global campaign, as well as the RAF technical and ground crews. So the title of my talk today is Cirrus Cloud Formation and Evolution from the Microscale to the Synoptic Scale. Here's the outline of my talk. It will start with the introduction of cirrus cloud and ice supersaturation, as well as the dataset and instrument that I will use for my analysis. For the first part of my analysis, it is the dynamical conditions of ice supersaturation in the extratropical upper troposphere and lower stratosphere. Two case studies will be compared with each other, and then a systematic analysis will be done to understand the favorable conditions for ice supersaturation formation around the thermal tropopause and the jet stream. The second part of my analysis will be the hemispheric comparisons for cirrus cloud formation and evolution. First, a method will be introduced to separate 5 evolution phases of the cirrus cloud formation. And then using this method, a comparison will be done for the cirrus cloud between the northern hemisphere and the southern hemisphere in terms of their microphysical properties and relative lifetime. The third part of my analysis is still an ongoing work that compares the observations from the aircraft with the cloud model. Finally, will be the conclusion and future work. When we look at the weather outside, for example today, we can feel the difference when the weather suddenly changed from a clear sky day to a cloudy day. For the climate system, clouds also play a very important role. In fact, one of the largest sources of uncertainties in current climate models are the cloud perturbations. Shown in this figure, which is derived from the IPCC AR5 2013, the top of the chart shows the anthropogenic greenhouse gas effect. That is the radiative forcing of such as carbon dioxide, methane, nitrous oxide. When we add up these anthropogenic greenhouse gas effects, their sum is about a positive 3 watt per meter square. And then we compare this value with the global cloud net forcing, which is the cooling effect of 20 watt per meter square. We can derive this simple equation that just a 15% change of the global cloud radiative forcing could either double or cancel out all the anthropogenic greenhouse gas effect. However, unfortunately, the current understanding of how cloud will respond to a changing climate is still very unclear. In fact, as shown in this gray color bar, the cloud adjustment due to aerosol still has so large an error bar. That means not only the magnitude, but also the direction of this value are still not well quantified. Among all the type of clouds, today I will talk about a special cloud that is higher in the altitude. It is called the cirrus cloud. The definition of it is cirrus clouds are composed entirely of ice crystals. It is located around 235 to 185 K. It covers up about 30% of the Earth's surface area. And for the radiative forcing of cirrus cloud, it's a combination of both warming and cooling effect, which is like it can act as a blanket that cover up the Earth to warm it up, and also it can block away the sunlight, which is like an umbrella. So the global net forcing for the cirrus cloud at top of atmosphere is a positive 5.4 watt per meter square. That is a result of the blocking of the short-wave radiation and trapping of the long-wave radiation. It is very challenging to simulate cirrus cloud in the climate models and also to estimate its radiative forcing. And this is partly due to that there are multi-scale processes that influence the radiative forcing effect of cirrus cloud. For example, it ranges from the microphysical properties, which include ice crystal concentration and size distribution, all the way to the macroscopic structure, such as the horizontal size and the vertical depth of the cirrus clouds. Besides the cirrus cloud its own radiative forcing on the climate model, on the climate system, it can also influence the climate by the dehydration of the upper troposphere. Shown in the lower left figure is an estimation of how the atmospheric radiative forcing will respond to a 1 ppmv change in water vapor. And just by the slight change in water vapor, we see that the peak of the radiative forcing change is around the troposphere, which is the most sensitive region. This is also where the cirrus clouds are usually formed. And this is why we have to understand why cirrus clouds form under certain conditions and how they are formed. In order to understand the formation of cirrus cloud, we first have to look at their birthplace, which is called the ice supersaturation. The definition of ice supersaturation is calculated by the relative humidity with respect to ice minus 1. And to calculate it, we need the water vapor pressure and the saturation vapor pressure with respect to ice. So as the prerequisite condition for ice crystal formation, we need to understand how ice supersaturation form, that is, the dynamical conditions of them. And shown by previous work of Penn and Monchak in 2011, using the remote sensing observations, they found that the tropopause height has a high correlation with the cirrus cloud top height. However, similar work hasn't been done to the birthplace of cirrus cloud, which is ice supersaturation, so it's still unclear if ice supersaturation would have a similar feature. In fact, there are a lack of analysis that relate the microscale properties of ice supersaturation with the synoptic scale dynamics. In order to understand ice supersaturation formation, the point that we have to understand the formation of ice supersaturation is because it plays a very important role in the atmosphere in the radiative forcing part. And this is to compare why it plays an important role in both cloud model and climate model. So this compares two scenarios. On the left-hand side is the cirrus cloud scenario, and on the right-hand side is a clear sky ice supersaturation scenario. For the cirrus cloud, as we can see, it can first block and reflect away some of the shortwave radiation, so it's like an umbrella. And on the other hand, it traps some of the outgoing long-wave radiation, which acts like a blanket. But compared with it, the ice supersaturation, although it also traps the long-wave radiation, it almost is transparent to the short-wave radiation. And if we do not allow ice supersaturation in cloud model or climate model, it will generate fake cirrus clouds in the model, and this difference could lead up to 3 Kelvin per day difference in the heating rate. Fortunately, the recent development in models has started to allow the ice supersaturation. These include both the cloud models and also the climate models. And because of these recent developments, it requires more observations to validate and improve these model simulations and parameterizations. Oops. Just touched the wrong button. And now we come to observation. When we talk about observations, there are a few major challenges. First, let's look at the in-situ observations. It has the advantage of high resolution and high accuracy and fast. But on the disadvantage part, it's usually lack of the sampling coverage in space and time. For the remote sensing observation, on the other hand, it has very well coverage over the globe, and also it has a continuous time sampling. But for the resolution, for example, the NASA Air satellite, it has a horizontal resolution of 45 by 45 kilometer, which is way larger than the median length of ice supersaturation of 1 kilometer that has been observed by the aircraft observation. On the other hand, the remote sensing observation usually suffers from the lower accuracy. For example, showing in this figure here is a validation of NASA Air's measurement using the HIPPO Global Campaign aircraft observation. And we can see there has been up to 40% water vapor difference between the aircraft data and the co-located AIRS data in the UTLS region. So because of these difficulties, there are still two main unresolved questions for how cirrus cloud and ice supersaturation form. The first question is, what are the dynamical conditions of cirrus cloud formation from the microscale to the synoptic scale? The second question is, are there any differences in cirrus cloud formation and evolution between the northern and southern hemisphere? So the analysis in my talk will be focusing on these two questions. To resolve the first part of the question of the dynamical conditions, I will use the dataset of NSF Starry campaign. That is a stratosphere-troposphere analysis of regional transport campaign. As shown here is the flight track of all 18 flights in Starry campaign. It have up to 120 hours and a resolution of 1 Hz, which is about 250 meters in the horizontal scale, since the aircraft travels at about 250 meters per second in the UTLS. The coverage of the flight is from April 21 to June 28 in 2008, and the sampling is mostly over North America. For the science objective, it is to understand the dynamical and chemical processes in the extratropical upper troposphere and lower stratosphere. And to note here, all my analyses in this work are restricted to temperature below and equal minus 40 C to make sure there are no supercooled liquid water. On the top figure here shows one typical flight that is transecting through the yellow surface, which is the thermal tropopause, as the black line shows the G5 track. And to understand the meteorology background of each flight, I relate the flight track with the NSAP GFS reanalysis data in order to understand the thermal tropopause height and wind speed. And for the resolution of this reanalysis data is 35 kilometers in horizontal and about 500 to 1,000 meters in vertical. One of the key measurements in the Starry campaign is the water vapor measurement, because we need to understand how much water vapor has been encountered. So measuring water vapor, I use the VCSEL hygrometer. It is the vertical cavity surface emitting laser. It's a near-infrared laser working at 25 Hz. For the analysis, I average it to 1 Hz to match with the temperature data. And the accuracy is below equal to 6%, precision below equal to 1%. The design of the VCSEL hygrometer tried to resolve two major challenges in water vapor measurement. First, the water vapor has a broad dynamic range in the atmosphere, all the way from 1 ppmv in the stratosphere to 40,000 ppmv to the surface. And to try to resolve this challenge, two absorption lines will be used in the VCSEL hygrometer. And the second challenge of measuring water vapor is water is a very high sticky gas that it has high affinity to the surfaces. So the VCSEL hygrometer uses an open path as shown here between the upper and lower mirror. So it will measure the air that is transporting through this open path. And as you can see, it's sitting on top of the NSI Gulfstream 5 research plane. And the part of the laser box is inside the plane, and part of the optical path is outside. Most of my PhD work has been involved with the lab calibration and also the field deployment of this hygrometer. Besides VCSEL hygrometer, there are many other instrumentation that we use for the analysis. That includes temperature, ice particle, carbon monoxide, ozone, vertical wind velocity, and total water content. Particularly, I want to point out combining the accuracy of water vapor and temperature, that is 6% from water vapor and 0.5 to about 1 Kelvin for temperature, we can derive an accuracy for the measurement of relative humidity with respect to ice from 8 to 18% under the range from -40°C to -77°C. And because 95% of the ice supersaturation happened above 59°C, it actually have a 8 to 16% accuracy. The first case study I will show in the Starlink campaign is from the research flight RF4. It happened on April 28, 2008. So this is a horizontal map at 300 hectopascal, where the darkest green line shows the maximum wind speed, horizontal wind speed. And then the light blue line here shows the geopotential height. Excuse me, just let me turn off here. And the dark black line here shows the flight track of the Gulfstream 5 aircraft. As we can see, it across the jet stream on both the cyclonic side and anticyclonic side. The big red dots upon this black line is where we see the ice supersaturation. And now I extrapolate the flight track into point A and B to take a look at the vertical cross-section. So on the left-hand side is the pressure in log scale versus horizontal in longitude. That's how we take the extrapolation into A and B. And the dot in light blue is where we see the thermal tropopause. The black line, again, is the flight track of G5. The red dots on the flight track is where the supersaturation happened. And here also I show the yellow crosses, which are the ice crystals on the flight track. So in this figure, it actually shows two major features of the dynamical condition for where we see supersaturation. First of all, we see that the supersaturation in red is mostly below the thermal tropopause. And secondly, it's on the anticyclonic side of the jet core. And using another figure on the right-hand side for the GFS data of vertical wind speed, the red color shows the positive uplifting and blue shows the negative downward motion. We see most of the ice supersaturation is correlated with this positive uplifting motion, which suggests a third feature that the mesoscale uplifting plays an important role in this case of how ice supersaturation is formed. Compared with the previous case, we show another case study of RF11, happened on May 14, 2008. Similarly, this is the horizontal map at 300 hectopascal, with the dark green contour shows the horizontal wind speed at the maximum. Now we extrapolate the flight track to A and B again and see the vertical cross-section, and we see that again the flight track is sampling both sides of the jet core, and compare with the previous case of RF4, these ice supersaturation is not way below the thermal tropopause, but actually around and below, slightly below the thermal tropopause. And the second point is they happen on both sides of the jet core, as both the anticyclonic side and the cyclonic side. And the most difference we see between the RF4 and RF11 is that for this RF11 case, when we compile the flight track with the GFS data of vertical velocity, not all the supersaturation happened at at uplifting motion. In fact, some of them are happening in this blue color downward motion. And this indicates that the small scale waves and turbulences actually plays an important role in this case for the formation of ice supersaturation. And when we compare the region where we see supersaturation, as I circled out here, with the region where has been theoretically shown that a lot of clear air turbulence would form, we see they actually match very well with each other. In order to further analyze this turbulence spectrum, I pick up the regions where we see the ice supersaturation that as we labeled as A, B, C, D. So this is the 4 segment of ice supersaturation observation. And now I did the discrete spectral intensity analysis for 4 regions and compiled them together into this log-log scale versus the frequency. So the black line, the dark black line shows the typical -5/3 slope that is typically observed for the inertial subrange of the turbulence spectrum. And there are 3 key findings in this figure. So the first of it is all ice supersaturation observation has the slope very close to this -5/3 line, which is the typical line for the inertial subrange. And second, if you look at the value of the slope, it's actually slightly steeper than the 1.67 value, which means that the turbulence cascade has not been fully developed yet. And
these are humidity spectra, or what they are showing, or temperature or velocity spectra?
Oh, sorry, I forgot to mention. This is the vertical wind speed spectrum at 25 Hertz. Thank you for mentioning that. And then when I compare the A, B, C, D 4 segments, we can see the segment A in blue has the highest spectral energy and dissipation rate. And this is highly likely due to the wave breaking events around the stratospheric intrusion, as the dark blue shows the PVU line, and here's the stratospheric intrusion. So besides the turbulence spectral analysis, I used the chemical tracer correlation to compare these 2 cases. And the tracer I used on the first row is the ozone versus CO, and the second row is ozone versus water vapor. First, in the RF4 case, we see ice supersaturation, which is the red here and the blue in this figure. They are following a horizontal mixing line, which suggests that the positive correlation has been observed for the troposphere mixing. On the right-hand column, for the RF11 case, the mixing line is a vertical direction, which is a negative correlation between the tracer, and that is suggesting a stratosphere-troposphere mixing. So using the tracer analysis, we see actually 2 different mixing scenarios happened between these 2 cases. And after the case study, another question of mine is, where are the favorable conditions that usually supersaturation would form? So here is the systematic analysis of all the flights in Starlo 8. So in this figure, it is the altitude with respect to tropopause on the y-axis versus the x-axis of the distance to tropopause break. The 0 degree shows where the tropopause break happened. And on this side is the equatorward of the tropopause break. And on the other side is the poleward of the tropopause break. And the data has been separated into clear sky and in-cloud data based on the C2 observations during the 1 Hertz aircraft measurement. So there are a few points I want to point out. First, you see the gray color here is where the ice supersaturation has 0 frequency in that bin. And when the color changes from light red to dark red, it means the frequency starts to increase from 0 all the way to 1. And for both cases of the clear sky and the in-cloud case, we see the supersaturation happen mostly below the thermal tropopause height. and the thermal tropopause height is illustrated in this thick black dot, and these light gray dots around it is the 10th and 90th percentile of the tropopause height. And the second thing is we see that our sampling is restricted mostly on the polar side of the tropopause break. Now, doing a comparison between the clear sky scenario and the in-cloud scenario, I plot their distribution in the tropopause coordinate, where 0 is the tropopause, and their probability is on the x-axis. The red line here shows the clear sky as supersaturation, and the dashed blue line here shows the in-cloud as supersaturation. As we can see, the difference is the clear sky as supersaturation peaks around the thermal tropopause, while the in-cloud one peaks at lower altitude. Now, besides the thermal tropopause condition, I take a look of how the polar jet core will influence the formation of ice supersaturation. But the first step is I have to define where the polar jet core is using the maximum horizontal wind speed. As shown on the left, I square out this region to find the jet core in the black box, and zoom in. I use these three criteria to define the jet core automatically. And these criteria include, first of all, you have to have horizontal wind speed greater and equal to 30 meters per second, and the maximum wind speed will be found along both longitude and latitude. And finally, they have to satisfy the condition of at least they are 100 kilometers in size, and also at least they are separated by 100 kilometers. And these criteria actually is based on the previous work, but has made some improvement. For example, the way that I find the jet core is based on three-dimensional wind field, both in vertical and horizontal. This is an improvement from the previous two-dimensional scenario that average out the vertical dimension. In addition, my criteria used both the longitudinal and latitudinal cross-section, which is an improvement compared with the longitudinal only searching method of many in 2011. So after defining where the jet core is, we can look at how ice supersaturation is located on the anticyclonic side and cyclonic side of the jet core. So here I define the negative distance in kilometer as the anticyclonic side, and the positive distance is the cyclonic side. And I separately plotted the distribution for ice crystal and ice supersaturation, ice crystal in gray bar and ice supersaturation in the hollow white bar. The first thing for ice supersaturation is the number of ice supersaturation on the anticyclonic side is 1.6 of the number on the cyclonic side. And similarly, this value is 1.3 for ice crystals. The result is inconsistent with the previous study using ECMWF model study of ice supersaturation, that more ice supersaturation happened on the anticyclonic side. Also, it is inconsistent with the Cirrus cloud observations that anticyclonic side is a more favorable condition. After all these regional dynamical analysis, if you remember, the second part of my question is, are there any differences in cirrus cloud formation between northern and southern hemisphere? In order to try to resolve this question, I use this hyperpole-to-pole observations HIPPO global campaign that happened from 2009 to 2011. It has a latitudinal coverage from 87 north to 67 south, and the vertical coverage about 600 transects from the surface to the upper troposphere and lower stratosphere. In total, it has a duration about 400 hours and the resolution about 200 meters. Shown in this figure is the flight track in yellow line of the flight campaign for all HIPPO. And to zoom in on the vertical cross-section, this figure shows the altitudinal versus latitudinal distribution of water vapor. And the red color shows where more water vapor is located, and the drier region is the dark purple and blue. And this is, remember, only one of the HAPO, and we have 5 HAPO in total. And before I jump into the question of comparing cirrus cloud formation and evolution, we first have to find a method. How do we define the evolution of cirrus clouds using the in-situ measurement? So this cartoon shows a scheme that usually the cirrus cloud is formed. So first it starts from the phase 1, which is a clear sky ice supersaturated region. It has no ice crystals. And then once the nucleation threshold is reached, ice crystal nucleation will happen, and this dark blue region is what I called ice crystal region, with continuous ice crystals observed. And as the ice crystal grow larger and larger, the region grow larger, we have an intersecting between the ice supersaturated region and the ice crystal region. This I call the early growth phase. And furthermore, as the ice crystal region take over the whole space, the ice supersaturation now become buried inside as a very small region. And this is what I call a later growth phase. Eventually, no supersaturation will exist because they are all used up, and only ice crystals exist. This is what I call a sedimentation sublimation phase. To illustrate this method, it is actually based on the length ratios between the ice supersaturated region and the ice crystal regions. For example, the clear sky ice supersaturation, we will see that supersaturation with respect to the whole region is 1 because it's all supersaturated. But ice crystal actually is 0 because there's no ice crystal. But once you start to form ice crystal, the ratio of ice crystal region start to become between 0 and 1. But the supersaturated region is still large enough to contain the whole space, so this ratio is still 1. And for the early growth phase, if you remember, it's the intersecting between the 2 regions. So both of them are between 0 and 1, and none of them is taking over the whole space. For the later growth, the ice crystal region totally take over the whole space, so it becomes 1, but the ice supersaturation region is within it. And eventually, there's 0 supersaturation, and the whole space are only ice crystals. And this is the number of each phase between the northern and southern hemisphere that I used HAPO data. So after we finally got the 5 evolutions of ice crystal formation, now we can take a look at individual phases. The first thing I want to take a look is the clear sky ice supersaturation distribution between the northern and southern hemisphere. The first figure shows the probability distribution versus for relative humidity with respect to ice between the red northern hemisphere and blue southern hemisphere. And remember, this is only for clear sky. And the second figure, compared to the first one, is a latitudinal versus pressure distribution. As you can imagine, it's like a transect of how a slice of the atmosphere show the distribution for ice supersaturation. The red means there's 0 supersaturation observed, and all the way to purple means all the observations in this bin is supersaturated. After doing a statistical significance test, I conclude that there are no statistical significant differences between the northern and southern hemisphere in the clear sky ice supersaturation frequency distribution based on HAPO global campaign. Please note that this is only using this HAPO global campaign. And compare with the previous publication of Overlas et al. In 2002 using the NCAR data, which is also a 1 Hertz aircraft data, but only from 2 locations at 55 North, which is Prestwick, Scotland, and 55 South, which is Punta Arenas in Chile. And their finding is southern hemisphere has higher clear sky ice supersaturation frequency. And I have to acknowledge that the difference between the work could both result from the difference in the geographical distribution and also the seasonal sampling. And I forgot to mention on the right-hand side is the log-scale observations for HAPO. As we can see, there's both significant amount of observations on both hemispheres. After taking a look at the clear sky distribution of ice supersaturation, now we can move on the entire evolution, which range from the red of clear sky supersaturation to phase 2 nucleation, and the green, which is early growth, blue, later growth, and finally purple, which is sedimentation and sublimation. And let me go through with you with the very complicated plot. So here is the relative humidity distribution with respect to the length of the ice supersaturated region. In this one, it means for clear sky ice supersaturated region, as the size of it grows, the magnitude of the RHI also increases with it. And for the nucleation and growth phases, this is the relative humidity versus the ice crystal region and ice supersaturation region spatial ratio. When it is 0.1 or 0.01, it means the ice crystal region are so small compared with the ice supersaturation region. It's very small and buried inside the large ice supersaturation region. And when it become 1, it means that they have the same size. But eventually, the ice crystal region will take over the space, so the ratio becomes 10. That means supersaturated region will become so small and buried inside the ice crystal region. And in this, the trend of the relative humidity is a decreasing trend, which is in agreement with the physical, understanding of how the ice crystal grow will take will take up the water vapor in the atmosphere, so the relative humidity will drop. And the last column shows only the sedimentation and sublimation. In this phase, no more supersaturation is observed, so everything is below 100%. And also, the way to understand it, the time of evolution is from the right-hand side to the left-hand side, that is from the larger ice crystal region, and dissipate into smaller ice crystal region. And as it dissipates into smaller ice crystal region, you can also see the distribution of the ice crystal widens, that more ice crystals will expand into both the dry region and also the moist region. And this is inconsistent with how the sedimentation will separate out the ice crystals into different vertical layers. So finally, after we understand of the trend of relative humidity evolution, we compare the first row with the second row between the northern hemisphere and southern hemisphere. And I understand it's hard to see from here eye to eye, so here is a more close comparison for the relative humidity. This is the first phase of clear sky ice supersaturation. This is the nucleation growth, and this is the sedimentation sublimation. As the thick, solid red line here shows northern hemisphere, and the dashed line here, red dashed line, shows the southern hemisphere. And the blue is with respect to the right-hand side axis, that is the difference in relative humidity. And the vertical bar here shows the 95% confidence interval. So if we take a look of all these three figures, the mean of relative humidity between northern and southern hemisphere are very close to each other, and their differences are always within the 95% interval for all 5 evolution phases. Similarly, we take a look for ice crystal number concentration and how it evolved during nucleation and growth between the northern hemisphere and southern hemisphere. For ice crystal number concentration, it has an increased trend as the ice crystal region keep growing, and it has a decreasing trend as the ice crystal region dissipate. And their difference again is within the 95% confidence interval between the northern and southern hemisphere. So no statistical significant differences has been observed. And the last comparison for the microphysical properties is the mean diameter, which is the number-weighted mean diameter for ice crystals. And between the northern and southern hemisphere for nucleation and growth, sedimentation, sublimation. If you just look at the difference on this line, blue line, it shows no statistical significance has been observed, and they are all within the 95% confidence interval. So besides the microphysical properties, another thing we look at is, does the lifetime of cirrus cloud show different features between the northern and southern hemisphere? In this case, I cannot tell you the absolute lifetime, so I use the relative lifetime. That is each phase with respect to the whole phase distribution, how much time of the cirrus cloud is spent in certain case. And we can see 30% of the time, a relative lifetime of cirrus cloud, are in the clear sky phase, and then it rushes through the nucleation, early growth, later growth really fast for only 10% of its lifetime. And most of its lifetime is spent in the final phase of sedimentation and sublimation, which is about 60%. And the red line shows northern hemisphere, and the blue with triangle shows southern hemisphere. And their comparison again shows no statistical significant differences has been observed even for the relative lifetime of cirrus cloud evolution. So finally, I want to show some ongoing work that has still been doing with Dr. George Brown and Hugh Morrison. So this is a comparison of the aircraft observations of ice supersaturation with a cloud resolving model. Let's first take a look on the left-hand side, which is the in-situ observation of ice supersaturation. I know this figure is very crowded, so please follow my lead. So the red dots here, it is the size of the ice supersaturation and their number of events. So this is the number distribution of the size. And the green triangle here shows the number of distribution for the spacing. So that is how separated they are from each other. And the blue hollow triangle here is with respect to the right axis. That is the maximum RHI increase as the length of the ice supersaturated region increase. So there are three main features from this figure. First, the median length of the ice supersaturated region, their length and the spacing are both around 1 kilometer. Second, there is an increasing trend of relative humidity as the size of the ice supersaturation increase. So now we take a look if the cloud resolving model can capture these three features. So this is using the CM1 simulation at 250 meter resolution, and this run is at 6 hours using a double moment scheme that allows ice supersaturation. And the thing we notice is, first of all, the CM1 captures the small-scale ice supersaturation region around 1 kilometer. But it doesn't show the large, very large ice supersaturation region down here, which is about 100 kilometers. But this could be related to this ideal case, which is a squall line scenario. And secondly, the CM1 also captures the increasing trend of the maximum RHI with the increasing length of ice supersaturation region, as we can see in this blue line. But we notice if you compare the slope, which is 3.3, with the slope, which is 14 here, we notice that this increasing trend is not steep enough. So this needs to be further analyzed in the future to check on the reason why. So finally, come to my conclusions. If you still remember, there are three parts of my analysis. It starts with the dynamical conditions of ice supersaturation in the extratropical upper troposphere, lower stratosphere. We compare two case studies. One of it is the mesoscale uplifting scenario versus the small-scale waves turbulences scenario. Second, we use the chemical tracer analysis to show that these scenarios are related with troposphere mixing and the stratosphere-troposphere mixing respectively. And for the distribution of ice supersaturation, we found that vertically is mostly confined by the thermal tropopause height, which is in agreement with the previous analysis of cirrus cloud height. And horizontally, it mostly happened on the anticyclonic side, which also is in agreement with the climate model simulation and the cirrus cloud observation. For the second part, I do the hemispheric comparison on the cirrus cloud formation and evolution. And after we compared several properties, we found both northern hemisphere and southern hemisphere have similar clear sky ice supersaturation frequency. In addition, they have similar evolution of relative humidity with respect to ice crystal number concentration, and ice crystal mean diameter. In addition, for the ongoing work, I showed a small one-slide comparison between the aircraft observations and a cloud resolving model, and we show that CM1 has the capability of capture small-scale ice supersaturation agents and also capture the increase in trend of RHI, and more analysis will be done. And as I show for the future work, I will compare more microphysical characteristics observed from the aircraft observations for ice supersaturation with more different scenarios of the cloud resolving model. And then I will also compare the observed feature of ice crystals and ice supersaturations with the climate model parameterizations. So that's about the conclusion. Related to this work, for the hemispheric comparison that has been recently published in the GRL, and for the dynamical condition, I'm currently preparing the manuscript for submission. So I would like to acknowledge again the help of my advisor, Dr. Yang Jensen, on my work, and also I would like to acknowledge the helpful discussions with all my collaborators. Besides my co-authors, I want to highlight Dr. Chris Davis and Dr. Rick Carbon that helped me with a lot of the analysis. And for the 2DC probe data, I want to acknowledge help from Chris Webster and Aaron Bessemer. And for the fast wind speed data, I want to acknowledge the help from Dr. Al Cooper and Pavel Ramashkin. So finally, during my PhD study and also my study here, I have received a lot of help from the research aviation facility, all the technical ground crews, and the scientists. So this is the end of my talk, and thank you for your attention. I would like to take any questions. Thank you.
Thank you, Minghui. Whoops.
For questions, if we can use the microphone here, or otherwise nobody can hear it on the remote sites and so on. So any questions? Yes.
Okay, my name is Ulrich Schumann. Was one of the coordinators of the INCAR experiment. Johann Ström and me, we organized the INCAR experiment. And I have to make clear, I think, that the objective was not to investigate the difference between Northern Hemisphere and Southern Hemisphere, but to investigate the difference in cirrus properties between polluted areas, which dominate in the Northern Hemisphere, and non-polluted areas, which dominate in the Southern Hemisphere. So we made clear that our correlations to the measurements were in clean air, which had very low aerosol concentrations, low ozone, NOx, CO2, CO concentrate, etc., compared to the Northern Hemisphere. And I think we saw there differences which were considerably, although we have to admit that from 40 hours of flight and 12 flights in the Southern Hemisphere, from Punta Arenas and 12 from Prestwick out to the North Atlantic or out to the Pacific, you cannot perhaps not conclude finally. But my question now is, can you relate your statistic analysis to aerosol concentrations? And can you see whether there's a correlation with that?
Thank you. That's a very great question. Actually, that will be the topic I will actually work on right next step after the first take a look at the comparison without considering each factors. So related to your statement, I totally agree. We think there are several factors that could influence the hemispheric comparison, such as the geographical distribution, where we sample it. Is it over land, over ocean? Which, cross-section we actually took a look at. And secondly is seasonal distribution. And third, aerosol distribution is definitely very important. In fact, one of the things that intrigued me is, although previously has been shown by aircraft observation, there is a 1 order of magnitude difference between the northern hemisphere aerosol loading and the southern hemisphere aerosol loading. But in this case, using the HIPPO data, although we only sample across the Central Pacific Ocean, we do not see a dramatic difference in the cirrus cloud formation and evolution. So that is an intriguing question to me. Does it mean that even though the aerosol number concentration is 10 times higher in the northern hemisphere, the effective ice nuclei between the two hemispheres might already have, for example, in the southern hemisphere, might already have efficient amount to activate ice nucleation and cirrus cloud formation, even though the total concentration is lower? But that's just my question. That's something I would like to answer. And just for one of the things I do look at, along HIPPO, we have black carbon measurement by the SP2 group, and I do see a difference between the clear sky ice supersaturation frequency with black carbon correlated or without black carbon. And the funny thing is I actually see more ice supersaturation frequency without the black carbon. And this is the part leads to another complication. During the aircraft observation, even though we measure certain type of aerosols, does it mean that that is the aerosol acting as an ISUKA? It probably is not. It's probably correlated with other aerosols as well. So that's some of my thoughts. I'm still trying to baffling with if I try to answer the question of aerosol, in fact. Thank you.
Okay, other questions? So I have a question. So what do you think the ice nuclei are for these situations? And in particular, if you really are having waves that are going up and down and you tend to nucleate ice particles as you move up, gradually they will sediment down and so on. So you're having a cleaning effect on the atmosphere from these cirrus clouds, at least if they occur very periodically and so on. So do you have an idea what nuclei were around?
That's very interesting question. So, although unfortunately we do not have ISUK like chemical content measurement during HIPPO, but for another flight campaign of the NASA campaign that they actually in one of my previous co-authored publication, Dr. Dan Sizzle has used the chemical content measurement for analyzing ice nuclei, which is what they call the ice crystal residue, to see what are the chemical content for the ice crystal formation, like the core of what happened inside ice crystals. And they found that there's a lot of sulfate and also metallic related particles. And that is an interesting finding that they almost find no bioaerosols, which in fact in the lab, maybe the bioaerosols could act as a very good ISUKA. But that leads to another question. In the lab, it's efficient. It might not be very ubiquitously observed in the atmosphere. So if in the future on the G5 we can have ISUKA measurement, that would be really nice. Trude?
Yep.
What do you think the fraction of ice crystal form homogeneously compared to heterogeneously?
Very good question. Again, if we want to compare these two scenarios, usually I would have to say we can speculate. Usually the homogeneous freezing would have more ice crystal number concentration with smaller sizes versus the heterogeneous scenario. I would think we probably observed both scenarios. For example, the previous case studies that are shown, the case that related with the mesoscale uplifting has 10 times more ice crystals than the case with the small scale turbulence and waves. But I do not have a fine criteria to say this one must be the heterogeneous equation and this one must be the homogeneous equation. One thing we can take a look is we use the relative humidity distribution and see how much of the relative humidity is below the homogeneous freezing line and the heterogeneous freezing line using the aerosol size of 0.5 micron. And in fact, that's also shown in the CISL paper. And using the HIPPO data as well as their NASA data, the combination of them shows almost very few cases are above the homogeneous freezing line, which posed another question. Well, at least we do not encounter during our observation into the homogeneous freezing line scenario. But it might not be the most direct demonstration because maybe we didn't sample it, or maybe when we sample it, it already happened. It already happened afterward. So these are all the questions we can only speculate using the current observation. At least we haven't encountered much. Thank you.
May I add one point?
Yep.
The relative humidity measurements depend on absolute temperature measurement, as you pointed out. And you also said that you estimated the absolute uncertainty of the temperature measurements to plus minus 0.5 and possibly even 1 K uncertainty, whereas the precision is in the 0.01 K range. I agree to these values in general. We have similar estimates for our measurements. 0.1 is 1 degree is a little much perhaps, but I recently compared our data to ECMWF data and to Radisson data, and I think that there could well be a 0.7 K bias in temperature measurements from aircraft. So, but if there's such a bias, that means about 50% relative humidity error, then one can perhaps correct it because the precision is so high. The one can simply subtract that or add that in the proper direction because it is repeatable. It's from flight to flight. It's the same from flight to flight. So you can correct for that. And that, of course, then changes all your humidity data. And that's perhaps interesting to look at.
Okay, thank you. Yeah, that's something interesting.
Okay, Al?
Al.
Yeah, I have a related comment. Very nice talk, but I'm concerned also about the error estimates. You gave us nice limits at the beginning, and then you didn't tell us any more about how your conclusions depend on those. You showed us instead a threshold and regions where you had ice supersaturation starting here and ending here. Have you investigated how those conclusions vary with your within the uncertainty limits that you have for your estimates? Could you have significantly larger regions if you're biased in the relative humidity, and could that affect your conclusions?
That's a very good question. Actually, I think about it. I haven't showed quantitatively the demonstration. So if we imagine some of the ice supersaturation, say it shouldn't exist for 115, it's actually 100%. Although, that's a very dramatic case. But if that's the scenario, as we can see, the relative humidity, in this case, it shows the maximum relative humidity, but also I tested the average mean relative humidity as an increase with the increase of the size of the ice supersaturation. We will see if we delete all the average relative humidity below 115%, we would probably not be able to see some of the small ice supersaturation regions. So that is like we're going to cut off the head of this part. But this trend of the distribution should still exist. So that's for the structural properties. And for the hemispheric comparisons, if we look at the difference between northern and southern hemisphere in terms of the relative humidity evolution between the 5 phases, let's focus on this blue line, which is the difference of relative humidity. And the vertical bar is the 95% confidence interval. We can see there is relatively about 8 to 15% for this vertical bar. And that gives us a little bit confident in the comparison, since it's on the same scale of the uncertainty estimation. But yes, It will be an interesting experiment to conduct to assume if we fluctuate our relative humidity plus minus 15% and see if the conclusions still hold.
Okay, thank you. I think we should stop it here, and thank you once again, Minghui. And Minghui will be around after the talk, hopefully for the next year or something like it. So you're very welcome to talk to her.
Thank you, Jan. Thanks for coming.